So Romero told me that I should go for 50 minutes from when he handed things off to me, so I guess I'll follow that one and aim for pretend, and I'll pretend I started at 11:30 by that clock. So so here's where we are. So at this point, we're connecting these three sorts of areas, which are Vey's Rosetta Stone, and we're trying to get information from one language into another, and at the end of last day, we were talking about how discriminants and discriminant complements, that if you have a problem involving some sort of discriminant, well, maybe more generally, there's a question of if you have some sort of family of problems that's nice in some sense, and this is extremely vague, and you let the problem go to infinity, the problem becomes nice. And because and many of these problems involve discriminants in the sense of if you're counting number fields, then the discriminant matters. If you're counting smooth curves, you might count all curves and throw out the singular ones. That's the discriminant too. And so these are the guys that somehow seem to stabilize, where all of this is meant to be vague, but there's a whole rich family of cognate examples that seem to exhibit this behavior. So I'd like to tell you about one more next. And last time, as a motivating example, we talked about polynomials, points on a line. That's polynomials in one variable. And then from that, points on a line, you could generalize to talk about configuration spaces, which I also discussed last time. But points on a line are also a special case of something else. They're hypersurfaces. They're cut up by one equation. So I'd like to tell you about a stabilization for hypersurfaces. But I think really I'd want to put this into some larger context. By telling you things we know that we in various fields that are all of the same flavor, that you should squint and see is the same thing. So maybe the motivating examples, well, the first one is going to be points on a line. The fact that polynomials, we can understand stabilization of various discriminants, and the answers are very nice. And here's another one which you would have seen, most of you had seen earlier in your life, which is I said, if I were to ask you what's the probability that an integer is square free. So it doesn't have a repeated prime factor. So that's the discriminant question. And as many of you will know, the probability is magically 6 over pi squared. And really the right answer is 1 over the Riemann zeta function evaluated at 2. So again, so the zeta function comes in here in a very arithmetic situation. And now here's something between algebraic, well, I guess it really is arithmetic geometry as opposed to arithmetic. And this is a theorem of Bjorn-Poonen, which really, both the theorem and really the proof has led to a great deal of interesting questions. So here's the question motivating it, which is, until this paper, we were missing the answer to the following problem. So let's say you have X is a projective variety over Fp, or over Fq. So many arguments in algebraic geometry will involve by slicing and do some induction by dimension. So in complex geometry, you've got a Bertini theorem, which says that because the complex numbers are so big, you can slice, if you have a smooth projective variety, I'm sorry, that should be smooth, then most hyperplane sections will intersect it smoothly. So you get something smooth of one dimension less. And the only problem with working over a fixed finite field, well, there are many problems from my point of view, but one problem is that there are only finitely many hyperplanes. And maybe if you're really unlucky, every single one of them slices X and the intersection is not smooth. So, but if you want to make these arguments work, they don't have to be hyperplanes. Maybe we should then try degree 2 hypersurfaces. But maybe you're unlucky and they all slice it singularly too. So it was not known. So the question is, does there exist some hypersurface of some degree in that projective space, we're in projective space, intersecting X in a smooth subvariety of dimension 1 less. So I mean, containing x is lame. We don't want that's not interesting. And so great. So that's and so. So what Poonen does is he wants to tell you that there is one, and so you would go to Bjorn and say, is there such a hyperplane? Is there a hyperplane? He'll say, I don't know. And then you'll say, is there a quadric? And he'll say, I don't know. Then you say, is there a cubic? And he'll say, I don't know. But he'll say, that's the wrong question. He can tell you. His theorem is about the odds that a random hypersurface slices X smoothly. So the odds that a hypersurface of degree d meets X smoothly, to say it informally. Again, he doesn't know the odds for any d, but he does know the limit as d goes to infinity, and it is non-zero. That means at some point there's going to be some hypersurface. So it's a really great way. It's completely non-constructive. Or I don't even know whether it's been made actually effective. If you could bound the d where it starts to get, where you can say, I know for sure by degree 95,000 that we'll find one meeting it smoothly. And even better than it being non-zero, it's non-zero because it is 1 over a V zeta value. I guess I always forget the, great. So in particular, if you compare this to the Riemann zeta function example of having really square free means smooth, that's zeta of 1 plus 1. And the integers are one-dimensional, so 1 plus 1 is 2. And so these things really are cognate to each other, although the proofs are necessarily completely different. Okay, so that's the arithmetic geometry version. And so now I'm going to go to topology. And so so in topology, we're up to around the fourth, let's see, this is the fourth example. So something that sounds very different. This is a theorem of Vasiliev. And I should say for reference, his ICM plenary lecture is the best place to look for this and all related things, although he thinks about it very differently. So here's what he says. He says, take the space of smooth divisors on C to the n. So in other words, and he's in the holomorphic category. So take all analytic functions on C to the n, and there are a lot of them, and look at where they vanish. So that's a huge infinite dimensional space. And he's going to tell you the topology of the space. And before you get alarmed, I should say that back here, back when talking about how many square-free integers there were, you were not alarmed because you were so used to the fact that, what do you mean the probability that is square-free? Well, what you mean is you have to take a limit and make sense of it and take a limit. And if you have one way of taking a limit and someone else has a way of taking a limit, as long as you're both reasonable people, you'll always get the same answer, even if the limits are slightly different. So this isn't alarming. So the question here is, the point here is you can make this into a topological space. And then he says the space of all divisors. And he wants just those that are smooth. So it really is a slicing. It really is a Bertini-esque theorem. And so the answer he's looking for is about cohomology groups, because that's the analog of, well, this is decades before Poonen. But and this space has two non-zero cohomology groups. H naught is 1, and if you think about it a little bit, you'll figure out what that number is, but it's a loop, well, let me not do that, and that's 1, and it's 0 otherwise. And so once again, it's kind of if that's AN, then the motive of, we saw polynomials in one variable, what are the odds, what's the space of polynomials with no double root? It had this behavior. This is a higher dimensional version. Okay, so now finally I'll say the motivic version and analog of these, which is this. Okay, so suppose you have X that's smooth, projective, or maybe quasi-projective if you care, a dimension n, and you have an ample line bundle, and I don't know of the backgrounds of everyone in the room, so really think it's in projective space and slice it if you want something really concrete. And then the probability that a section of L to the n, I need a new number, m, no, I don't want that because I'm going to use m in a second. Oh, I'm running out of letters. To the z, that's a really bad choice, but okay, is smooth. In other words, a slice. Think just of Punin's result, where you're taking that it's smooth. That it even better has. This is getting messier and messier. Has exactly m singularities. Well, great. So what do I mean by this, even before I go on? Because because this is ample, which I didn't write down either, because it's ample, eventually when you take a really big power, then you know there are going to be lots of sections, and the space of sections will be a projective space. And so what do I mean? What I mean is in that projective space of divisors, how many of those divisors have exactly m singularities? And I want to make that into a fraction. Where's my fraction living? It's in the Grothendieck ring, localized at L, completed. So we're back in the. So the question is, what is it in the Grothendieck ring? And the limit as z gets big is 1 over the motivic zeta function. It's a motivic zeta value of the dimension of x plus 1. Which is, again, you should look very much like, I'll go back to Punin's result, and I'll go back to, what's that? M, yes, no, I'm sorry. Yes, that's m equals 0. So let me say what the numerator is. Well, in the denominator, you know what this is? This is the generating function for I need more and more letters. So that t is taken to the kx. Okay, good. So far, I'm not many letters left, but I'm sure I can be okay. So, and the numerator is going to be something we saw last day, which is the generating function, not for all of not of all of sim k of x, but instead where you have exactly m parts, exactly m points with multiplicity. So it's exactly the same numerator, and now I'm evaluating this at t equals L to the minus n minus 1. So it's exactly the same numerator, but evaluated evaluated at a different value of t. So the denominator is a zeta value, and the numerator, I should say, can be expressed cheaply with just minor bit of work as a zeta value. So and so that means we know precisely what it is, and in many ways it suggests things that are different than. So it's motivated by what we know in these other fields, but it then tells you things that should be true in these other fields, which are actually verifiable. So before saying what that is, let me make some remarks on this theorem. One is that it's, and I should say as my standing assumption that all new ideas are joint with Melanie Wood continues and will only end maybe near the very end of this lecture, but may never end. The first remark is that, okay, you're absolutely right in saying this should depend on M, and it does, but it doesn't depend on L. We just want something, the way I think about this is you should really see this as a limit as L gets really, really ample. Secondly, and that's a common feature of things like this. Secondly, I think maybe not in this room, but in most places, in complex geometry, let me say, the interesting case would be complex varieties. But the proof for complex varieties goes through finite fields. So the proof you need to know. You need to be able to do this for finite. The proof needs finite fields, even if you're a complex geometer. But no one in the room probably is a complex geometer, so you may not care. And then if m is 0, and that's what I'd written down, so I spoiled it already. You're looking for smooth. The case of smooth, there are no singularities, and as with yesterday, there's only way to divide k into 0 parts is if k is 0. And we get 1 over the zeta function. So this is exactly That's exactly what we saw twice before. But I want to say that we get the same answer in quotes, but it's logically, the proof is logically independent, and it does not imply Poonin's result, nor does Poonin's result imply this, because both involve limits in different ways. Yes, thank you, +1. Great. And then furthermore, it suggests it suggests what you should expect in all these other fields. So enhanced versions well, okay, let me mention a few. It suggests that there should be an enhanced version of Poonin's result, where it's going to tell you not just what are the odds of a hypersurface being smooth. We should be able to, over finite fields, you could dream that you could say, what are the odds of it having exactly m singularities? And the answer should somehow be the same. We have a prediction as to what it is. So, and in fact, so in fact, the week before coming here, Joseph Gunther, who's in my working group, but this happened even before the week started, actually proved it in like a really, it feels it's very much the right way. The hope is not to try to compute both sides and show they're the same, but have some reason as to why they should be the same. So this happened. So this is a very recent thing. So this was predicted and then answered. But here's something which is predicted and not yet answered, or partially answered, which is in complex geometry. You could take so Vasilyev's theorem is about c to the n, and it's just about functions on c to the n divisors. But really, you should see that the line bundle, there's only one line bundle, O, the structure sheaf, the trivial bundle, and I want to take the limit, and that is ample. If you say what you mean by ample, and I want to take bigger and bigger powers of it, but it's still always O. So the limit, there's no limit involved there. But this suggests that you should generalize this to take something, this is now geometric in complex geometry, that take something which is quasi-projective and an ample bundle on it, and the statement should be that if you take the number of sections, maybe make them algebraic, or if it's compact, then compact is a bad thing to do. There won't be that many functions. If you take the sections and ask when are they singular, or when do they have even m singularities? But let me just even talk about when they're smooth, have no singularities. Then what it suggests is maybe the first order. Well, it suggests that these spaces, as L gets bigger and bigger, stabilize. And what does that mean? It means that the topology should get better and better. What does that mean? It means that you should be able to read off the cohomology groups will begin to stabilize and should be predicted from number theory, and even better, the homotopy types should stabilize in some sense. And so there are a bunch of explicit statements you can make. For example, if you take the space of smooth degree plane curves in P2, then the space of them, it's a bigger and bigger space, but the cohomology groups stabilize to, so here's smooth plane curves, the moduli space of smooth plane curves. This theorem predicts that there should be, in the end, cohomology at 4 places in codimension 0, 3, 5, and 8. And when you see that, you should believe there should be a cohomology class in 3 and in 5, and they should square to 0, and they should multiply each other to get the 8. And this, in fact, is proved by Ursula Tomasi. And she's done more to really get a hold of, in homogeneous cases, to really prove what's predicted and say even better things. And then also, I should say, the work that I mentioned before of Sandra Coopers, Jeremy Miller, and Tran is also answers a lot of predictions, proves a lot of predictions. And I should say that their methods have to be different. This can only predict, but then they can actually prove things. And maybe because this is a place for young people, especially graduate students, I want to point out that all of these things that I'm describing are, every single author is either a graduate student or was a graduate student or was pre-tenure track or maybe Yeah, I think no one was even tenure track at the time they had these ideas. So so there are really fundamental things that are out there if you know things other people don't, and you find the right problem to use your expertise on. Great. Okay, good. So I now want to take this point of view somewhere different, and so here's a motivating question. So this is, I don't know what to exactly call this. I'm going to call it. So sort of this. There's a whole area of ideas that somehow began to break open with Manjul Bhargava's work, and so let me give a motivating example. And so fix a positive integer d, even bigger than 1 even, and I want to ask how many number fields of degree d are there? And of course the answer is an infinite number. That's why I made d bigger than 1. So that's of course a stupid question, but then of course you say, well, how do you count them? And there's only one reasonable way of counting them, which is by discriminant. So the question is basically, how does it grow with discriminant? So in other words, how many number fields have discriminant less than capital N, say, and we'll let capital N go to infinity. And so in small cases, we know that in fact it grows like a multiple of n. It's linear. And I'll worry about small cases later. And it's certainly conjectured or believed that this should work for any degree. So for d equals 2 and 3, this was known classically, and then Bhargava proved it for 4 and 5 using sort of very dramatic, and reinterpreted 3 using something very dramatic. And the answers, this coefficient of how many there are, involve the Riemann zeta function, Riemann zeta values. And a little bit more, there's things that, and relatives of Riemann zeta values. So great, once again, we're asking for a number. We're keeping track of discriminants, we're taking limits, we're counting things, and zeta values come up. So if you squint, this should fit into the same story as well. And now I want to mention things about Bhargava's proof, or his approach, which is the way in which his argument works, although it's not necessarily directly presented that way, involves very classical, I guess means pre-Bhargava, but even much older things, approaches, even in the cases where n is 4 and 5. And he realized how to use this geometry to great advantage. I should say at the very end of the work, of the argument, then he has to do some geometry of numbers, hard stuff, which is specific to geometry of numbers. And when we go on to talk about this, somehow everything will be cognate in different fields, except at the very end where there's different things that you have to, different directions you have to go that are the same complexity, but are specific to the field. So let me give you a geometric picture of what's going on. So let me give you a geometric picture of how of how you might count, about how you might count. So let me start with, let's say we know, so this is now going to be spec z, so it's a smooth curve, and the number field, there's spec q, the generic point. And so if you have a field extension, say a degree 2 field extension, it's going to look like it's going to have, the ring of integers will be a nice smooth curve double covering that. And again, if you're not fluent in this language, just, I'm not going to, follow it just intuitively. And if you're looking for cubic number fields, then it'll be a degree 3 kind of thing. And if you're looking for quartic, then of course, well, great, it'll be degree 4. And so how do you get, so what I want to do is count these. So let's say we already know how to do this just for simplicity. Well, we do know how to do these. We know the quadratic extensions of Q, and we want to do these and we want to do these. So what we do is we somehow find some way of reducing it to a previous problem. And you've seen this before because you know how to solve, well, no, you may not know, people know how to solve a cubic equation over Q, and there's a recipe, and you first solve a quadratic, and then you take a cube root. And the quartic, the recipe is to first produce a cubic, and then inductively know what's going on with the cubic. So let me explain this geometrically. So the Galois, what I'm going to say is, from one point of view, Galois theory, which you've seen, S4 is a solvable group, but I want to sort of add a geometric picture to this too. So how do I go from, let me just do from 4 to 3 to make things, to show you the most complicated situation. So when I see this picture, I've got four sheets, A, B, C, and D, let me call them. Oh, sure, was that a question? Nope. I see they're watching me on the screen up there, or maybe it's Princess Elsa is the, so I've got 4 sheets, but this is a branched cover. So when I go around one of the branch points, I permute those 4 sheets in some way. And so now I'm going to tell you a triple cover, and it's going to have exactly the same branch points, and all I need to do to tell you the cover is to tell you those three things and how they behave under going around that branch point. So now let me just give names to these, to the 3 sheets. This one's name is going to be AB plus CD. This one is going to be AC plus BD. And this one is going to be AD plus BC. And so when I go around a branch point, I'm permuting the letters of A through D, and that means I'll be permuting these 3 guys too. The way I like to think about this is you have A, B, C, D, that gives, this is a tetrahedron. The 4 points kind of in a tetrahedron, and then these are the 3 different ways of picking the opposite pairs of picking a pair of opposite edges. And so there we go, that's a triple cover. And then that's exactly what's happening in Galois theory, where you get the S3 extension from the S4 extension. And similarly from here, if this was XYZ, you go to the 2 cyclic things, XYZ and XZX, XZY. So that's the picture. But let me make it even more geometric, which is when you have 3 things, a cover like that, it naturally sits inside a P1 bundle over spec Z. And I'm deliberately not going to write spec Z because spec Z is not relevant at all. This is a very general, what he's doing there is very general, works over any base. And if you have 3 points, then they naturally sit in a P1 bundle. And so you really have this living in some kind of P1 bundle. And if you have 4 points, and I'll say more about this in a second, it'll naturally sit in some sort of P2 bundle. And if I've got 3 points in P1, that's cut out by a cubic. If I've got 4 points in P2, then in general, that's cut out by 2 quadrics. And so you can really somehow parameterize things. If you have to parameterize the cubics in P1, you know how to do that. But you want them to be singular, not smooth maybe. And if you want to parameterize 4 points in P2, in general, you just need to choose 2 quadrics or a pencil of conics. Okay, so I'm getting a bit, fuzzy, and so I will get, well, fuzzy in a different way, which is, what's the function field analog of this? Well, instead of spec Z, we're going to take P1. And so the corresponding problem involves counting triple covers, double covers, quadruple covers. These are called, in the case of degree 3 covers, these are called trigonal covers. And I should say geometrically what you really want to count is you want to mod out by the automorphisms of the base, because the same curve can cover P1. You could, if you have a cover, you could slide it around by an automorphism of the base. And so this is exactly the same question, and the fact that this is an old sounding name shows that objects like this have been studied for, have been relevant for 200 years. And so there's a space of trigonal curves, and now we want to let the discriminant go to infinity. So we want the number of branch points to go to infinity. Well, by the Riemann-Hurwitz formula, that means the genus goes to infinity at the source curve. So now we have something now we have an explicit question. The space of all trigonal curves of genus G, we want that motive. We want to let G go to infinity. And similarly for, I guess, for all degrees. And the answer, which is that in the trigonal case, we can do it. And the answer you write is in terms of motivic zeta values. And for the tetragonal, and it's completely analogous. Tetragonal, no one knows what that means. that means degree 4, and you can do the same thing. And again, you get motivic zeta values and some other funny stuff that's funny in the same way as Bargov gets it. And he can also do pentagonal, degree 5. But he has to go through contortions to make it work. And in theory, the same thing should work too. And just doing it would be not very much fun, and it should work. And it should work too. But now, based on this, Bhargava conjectured an answer in the arithmetic case for general D. He can tell you he can tell you what he predicts will be the number of degree D extensions of Q. And it's a beautiful answer with a lot of zeta values in the formula. And how did he get that? Well, he kind of played name that tune. He was able to look at the first few cases and say, oh, look, the pattern continues. And so he conjectured this. It's a wonderful conjecture. But if you believe that conjecture, then and you translate it to the motivic side, what this suggests is that the space of diagonal curves, that motive stabilizes in an appropriate sense, which means that they eventually become all stably birational to each other. And this connects to a long-standing question in geometry, which is we've been able to solve, we know that these guys are all unirational, and people have been stuck on degree equals 6 for a very long time. This was from the 1920s, and some of the difficulty here is exactly the same reason that Bhargava's results get stuck a little bit at 6. And so it's not being able to show that degree 6 covers of really high genus that it's unirational, or put it in terms of counting points. We don't know how to count degree 6 covers. And now some people, so what if you believe Bhargava's conjecture, you would also believe, you have to believe, because there's no difference in the situations, that these guys actually do all become stably rational eventually, which is a very outrageous prediction. And if you ask a geometer about this, they will say, I don't believe it because these arguments involved a very special geometry of small numbers. So that's the only reason it worked out nicely. But if you disbelieve this, you have to disbelieve Bhargava's conjecture as well. So this is where geometry is predicting, well, potentially, geometry is predicting something about the arithmetic is predicting something about the geometry, and they disagree. So there's an interesting, that tension leads to some interesting things which can be checked. Okay, so okay, so before I tell you the geometry of how this is done, let me mention another problem, which is we can do a motivic count of these, and I've told you about that. But you might also say you count point count. So this is the other. We can do all of our standard at all of our natural realizations. And instead, you can do this over FQ. And the only problem, so in other words, the question is this: how many trigonal curves are there over FQ? Literally, just tell me that number. And the expected answer, form of the answer should be, well, I don't know, but when G goes to infinity, it's going to tend to this. And so, and one should dream that the story should be parallel to the motivic story and the arithmetic story. And in the PhD thesis of a student of Jordan Ellenberg, Zhao, he did the trigonal case, and I believe that soon, this is one of the working groups, will successfully, at this point what they've done leads me to believe that they can't lose, that they will, that will also know it in this case. And the interesting thing is the comparison between these different worlds. And let me tell you something interesting about the comparison that's surprising, which is, this is Bhargava's right there. So, so when you're counting counting quartic fields, well, if you ask me, if you take a random quartic field, what's its Galois group? I would say S4, of course, that's the generic Galois group. Now, the amazing, strange fact is that, in fact, with positive probability, the Galois group is D4. So the way I like to think about it is if you take a random, it's like a random quartic means you're trying to construct something with ruler and compass. You can construct with ruler and compass a positive probability of the time for some reason. So that's very mysterious because I feel that that's unexpected, although retroactively Cohen-Lenstra heuristics can be made to predict it. But on the motivic side, it doesn't turn up because the D4 extensions are kind of really high codimension. They get higher and higher codimension. And the reason there's a disagreement is because as the genus gets bigger and bigger, the D4 locus gets higher and higher codimension, but it breaks up into lots and lots of components. And somehow the high codimension versus number of components match perfectly to make them both contribute the same amount, the same order in the Bhargava setting. But in Zhao's case, this I only know as of last night, thanks to the group that's doing the quartic fields, that's doing the degree 4 case, that already turns up here, where the answers are different because there are things that are large codimension that somehow, but there get to be more and more of them. So I don't want to say too much more because there's no way you could digest what I'm saying in real time, but I want to get across that there's sort of all sorts of interesting structures and reasons for differences in predictions between these three worlds. And maybe one last question I want to ask, which I also had peddled to my group as something to do, but it's a geometry of numbers thing and perhaps less suited for people who are likely to be at this particular Arizona Winter School. My question would be, how many genus 2 curves are there over Q? And then, of course, you make sense of this in the only possible way you can, which is, well, they're an infinite number, but of course, you can order them by discriminant. Everyone has a discriminant, and so just how many are there as n goes to infinity? That should be an answerable question. How many genus 3 curves are there? Are most genus 3 curves? Is it true that they're almost all, that none of them are hyperelliptic? Or is there something funny happen, like when you're counting points? There are all sorts of questions over Q that I think are not explored, partially because the people who are asking the questions tend to be in this side of the world rather than this side of the world. Okay, so what's the idea for this counting? Well, let me tell you where these bundles come from. So if you have a degree 3 extension, a degree 3 cover, call it what you will, because I'm carefully not telling you what category I'm in. It doesn't matter. And so here's where you get this P1 bundle from. It's a canonical embedding. So what it is let me put it this way. I'm going to map to. So the functions on here. Let's say this is okay. Let's make this Z and make this okay. So this is a free Z module. In this case, it's Z3. That's just because there are not many free three-dimensional 3Z modules. But in general, if Z is more interesting, well, nothing's more interesting than Z. But if Z were more interesting, then it would be a twisty bundle. And so if you projectivize it, there's your P1. There's your oh, whoops, sorry, that is not right. That's a P2 bundle. But there's a trace map. So this is a rank 3. It's rank 3, but there's a trace map. And so you can reduce it to rank 2 by looking at the trace 0 ones. And then you projectivize that free module, and you get a P1 bundle. And if you go through everything, that just tells you that your points naturally sit inside some P1 bundle. And the same game works in any degree, that if you have a rank, so if it's degree 4, you're going to get 4 points in a P2 bundle. If you have 5, then you have 5 points in a P3 bundle, and so forth. And now you can begin to parameterize. If you want to know all the tetragonal covers, you need to understand all the sets of 4 points in a P2 bundle. And what is that? Well, if you know what the P2 bundles are, you have to just figure out how to all the different P2 bundles and all the way to intersect families of two conics in that P2 bundle, and that will give you it. And if you want to go back to solving quartic equations, here's how you go from degree 4 to degree 3. That's going to bring back the tetrahedron, which is if I give you 4 points in P2, well, then I have a two-dimensional vector space, a P1's worth of conics through them. So there's one of the conics through them. There's another conic through them. And so there we go. We have a P1 corresponding to that. And in that P1 of all the conics through 4 points, 3 of them are singular. So now we're into the discriminant. I should say much of Tony's lecture is going to secretly be here. So you have 4 points. There are 3 conics through these 4 points that are singular. that's 1. You basically pair the points up in different ways, in all possible ways. And so so in other words, in this P1 of all conics, there are 3 points. And we're exactly back in this case here. And that's how that dictionary goes. Okay, so now, so I want to give you, maybe I should say one more thing, which is, why is it that solving a quintic is very hard, and quartics are not? Quartics, we can use geometry, and I told you there's geometry with quintics. So why, therefore, can we not solve a quintic equation in radicals, or what's different about 5? Well, if you have 5 points in P3, you are kind of, if you have 5 points in P3, you can't make it a complete intersection, because 5 is, you can't intersect 3 hypersurfaces and get something of degree 5. So you need to do something else, and I'll give you the clue in just right now by trying to convince you that this is part of a larger story. So I'm going to make a table where and the magic name here is Mukai, as before. So let me see if I can. So 2. I'm going to go to 7, 2, 3, 4, 5, 6, 7. You'll see in a second why I'm putting this here. And now maybe let me do the K3. So K3s have been K3s are we've talked about a lot this week. And so let me write down the K3s, which is the K3. Better make sure I align these with numbers correctly. So a K3, I think that's where I want to put it. Okay, so you can have a degree 4 K3, and that is a quartic in P3. Degree 6, that's a intersection of a quadric and a cubic hypersurface in P4. Degree 8, it's the intersection of 3 quadrics in P5. And there's also degree 2, which is a double cover of P2 branched over a sextic, as we saw last time. Okay, good. So let me say something else and give you a whole series of examples, which is now one very close are canonical curves, Riemann surfaces. Riemann surfaces are classified by genus, as you know, and how do you then get at the moduli space? You take the curve and you canonically embed it in projective space using its differentials. And so it turns out that most genus 3 curves are degree 4 curves in P2. Most all genus 2 curves are double covers of P1. Genus 4, quadric intersect cubic in P3. Genus 5, there is intersection of 3 quadrics in P4. Okay, so this is sort of like a slice of that. Well, here's something else which is not quite slicing, which is let me do points. Let's do number fields. So number fields, I said 3 points give you something which is cut out by a cubic. I need to put this here. So 3 points, I have my numbers slightly screwed up. 3 points, I wanted that to be the 3. 3 points is really a cubic in P1. 4 points is the intersection of 2 quadrics in P2. And 2 points, well, that's a little bit trickier to say, but I really think of this as 2 points in P0. So it's so we have 2 points inside P0. And then my last in this family, although there are more, it's elliptic curves. Now I want to keep track of, cubic elliptic curves in the plane are, so genus, what is a cubic curve in P2? You know it's genus 1, and you want to say it's an elliptic curve, but you haven't picked a point. So really it's a genus 1 curve with a degree 3 line bundle. So this is genus 1 with degree 3 line bundle. Well, that's a cubic in P2. What if you have a degree 3? What if you take a degree 4 line bundle, and it maps into P3, it's the intersection of 2 quadrics. And let's go back to degree 2, and what do you get? Well, degree 2 will give you a 2-to-1 cover of P1. And so as you see, there are these things which seem to go, which are very much in parallel. And now the interesting thing is you can actually go farther. And so well, let me put a question mark here, because that's the thing that I will tell you about sextic field extensions, sextic number fields. And here's how you go. And so here's how you go farther. So now I will finally tell you how to get a hold of genus 6 curves. I'll tell you how to get a hold of K3s of degree 10. And also I will tell you to get 5 points, quintic field extensions, and genus 1 curves with degree 5 line bundles. So what you do, it can't be, you couldn't make it a complete intersection in any of these cases, but you can do the following magical thing, which is you have the Grassmannian of 2 planes in 5 space. This is a 3-dimensional thing, and it sits naturally inside P9 by the Plicker embedding. And it's, did I mess up? Oh, I said 6 and wrote 3. Great. So I hope that's right now. And I hope that's right. I should, maybe I should look at my notes to be sure. Good. Great. And now, what's its degree? Its degree is 5. It's cut up. And so if you were to take this and slice it with random hyperplanes, so it's in P9, and let's slice it with, let's see which one I want to do first. Let me slice it with 6 hyperplanes. Well, let me slice it with 5 hyperplanes. Then we're going to get a curve that's degree 5 in P4. That's what goes here. If we sliced it with 6 hyperplanes, we get 5 points in P5, in P3. And that's what Bhargava uses, although he would describe it differently. This is cut out by quadratic equations, which can be described as, well, if you know the word Pfaffian, that's what it is. But you could believe the Grassmannian has beautiful Plicker equations, and they are all quadratic, and that's what you use. So if you want to parameterize 5 points in P3 up to isomorphism, you might as well just take the Grassmannian and slice it and parameterize it modulo a bigger group. And I've just told you in a nutshell what makes the quintic fields work. But then this goes on. Well, I should say now, how do you get the K3s? And why is the story better one step up for canonical curves and K3s? What if you instead slice with a quadric? So now it's degree 10 by Bezout's theorem. Its dimension is 5 because you've sliced with a degree 2 hypersurface, but it's still inside P9. And now I want to slice it down by 3 hyperplanes. And that will knock this down to dimension 2, and this will knock this down to P6. And now you have, and I hope this is going to be in the right space, unless I've made an adding error, then the resulting thing is going to be a K3 surface. And those are all of your degree 10 K3s. And so if you want to understand that moduli space, you now have you do intersection theory not in projective space, but inside this homogeneous space. And if you take one more hyperplane, then you knock the dimension down one more, and you get a canonical curve, a curve of genus 6. So essentially all genus 6 curves can be described in this way. So if you want to understand the moduli space, this is a way to do it. And it doesn't stop there. Mackay has something that goes, depending on which road you go, goes very far. Well, I don't know what you mean by, well, I don't know what I mean by very far, but maybe to around here. So what this means is that there's a whole lot more mileage potentially to be gotten, and different people are getting mileage in different ways. Julien Lee and collaborators, Francois Greer and I think Jiu Tian, I have to think, are able to understand the space of K3s in low degree very, very well and prove theorems about the left-hand theorems using this. And so I think what this should make you want to do, oh, maybe I should say what the homogeneous spaces are and why they run out. So you have the Grassmannian G25, which is degree 5 in P9. This tells you about 6 points, sextic extensions. The next one is the orthogonal Grassmannian And these all look like kind of accidents. Well, they are accidents. They're these magic of small numbers, but they're 14, I think. And it goes on. And at some point, your luck runs out. This does end. And the reason why is because there are very few codimension 3 things that are degree 5. And there are even fewer codimension 4 things that are degree whatever this is. And so that's why we're lucky. But the luck didn't run out at 5 or 6, at 5 points. Or we're luckier for a while longer, and no one, I think we've not sufficiently mined what Mukai has found us, has given us down to here. So let me just sum up the last 4 lectures. Maybe one last thing before summing up is I should go back to this table and say that when Tony was talking about K3 surfaces in the Brouwer group and this amazing paper of Van Hemen, if there were a lecture 5 would be the same as Tony's lecture 5 because we talk about the same things, and the K3 surfaces are going to be these K3 surfaces, and the corresponding elliptic curves are these elliptic curves over the function field, and all those calculations in the Brouwer group exactly are also inside the story as well. But for the sake of time, I won't say anything more about that, other than to say that I agree that Van Hemen's paper is a gem. I just don't know how to pronounce his name correctly because I'm not Dutch, despite what I said at the start of the first lecture. And at the first lecture, I told you about the Grothendieck ring. So the things I want you to ideally remember is this thing called a Grothendieck ring. It's got a simple definition, and it's hard to understand. And it's a very blunt tool, because you're only cutting and pasting and taking products. And this ring is sort of simultaneously interesting geometrically and over finite fields. And you can prove things using, for example, Bittner's presentation. So you can really, and we did even do it to prove things about weights. Deline's theory of weights can be understood well in this way. It leads us to the right way to think about Weil conjectures. And basically every conjecture about this ring appears to be wrong. But they're all wrong for interesting reasons. And they all have to do with sort of geometry and arithmetic simultaneously. And so maybe the right ring is the Grothendieck ring, localized at L and completed. And it's maybe the right thing for many things. And that means that maybe L not being a zero divisor, this is Borisov's result, is actually our friend, not our enemy, because this was a badly behaved ring, and by inverting L, suddenly things become nice. And for people who know about stacks, by putting this here, you can even have a Grothendieck ring for stacks, and it's the same thing. And then essentially, when do you use this ring? When does this come up? Whenever something is true for some very blunt reason, for some motivic reasons, then you should hope to try to prove it in this ring or some modification of it. So it's a blunt tool, and you use it when blunt tools seem to be called for. But with this blunt tool, facts and topology about stabilization now can have an algebra arithmetic incarnation, and you can try to work out how stabilization works in this blunt ring. And if you get stabilization here, you should believe it when you're counting points or over Q or in topology with cohomology groups. So stabilization in the Grothendieck ring is for that reason an important question and testing ground. And we saw as examples of where we could apply it are things like configuration spaces or hypersurfaces or trigonal curves, or applied in or we can apply it in the Bargavology case. And so as a result, there's sort of it's hard to prove things about this ring, but it's really great to be able to use this ring to actually tell you new things, either provably or conjecturally. Okay, so thank you very much for